Yeah. Okay. So huge pleasure to welcome Greg Yang here in TFR. So a little about Greg. He's been at Microsoft Research, and he's been laying foundations for theory in large-scale deep learning. So much so that you can be sure that even 10, 15 years later, these ideas will be guiding practice in deep learning potential. I've requested him to kind of give a brief introduction to deep learning for many of you who don't know. So hopefully that will be a great addition. Now, he received his, a Morgan Prize in 2018. And there are many things to like about Greg from our brief interactions, but one amongst them is that, he kind of never felt that need to have a PhD. Because the viewpoint is whatever you need to learn, you can learn on your own. Why do you need to go through the whole process of PhD? So he's doing excellent work, and we look forward to your talk.
Yeah, thanks indeed. Thanks for having me here. That's a great location. Love the ocean view. Okay, so how many of you have already seen neural networks before? How many of you haven't seen neural networks? How many of you don't know what deep learning is? Okay, so it's just for you. Let's look at what a neural network is. So just a brief review of neural networks. So the idea is a very old idea, going back to the mid 20th century. But the point is that we're like mimicking a real neural network where a signal propagates from one layer of neurons to the next. So here you see some kind of like directed graph, right? And there's like 3 layers of nodes in here, and so the first layer is called the input layer, and then the last layer is called the output layer. The middle layer is called the hidden layer. So the point here is that like if you're in the outside, for example, if I'm talking to you, then I only see like vision, like images from around the world, and that will come in to the input layer, and then I will speak or I will like interact, and that is the output layer. But in the middle, there's some processing going on in my brain. Now you don't see directly, so this is representing the hidden computation done in the brain, and each node in such a layer is called a neuron. And and the way the signal propagates in such a neuron, such a neural network, is that like the neurons in one layer connects to the neuron in the next layer, and each connection has some string to it. So for example, like this neuron connects to this neuron with string 2, and then this other neuron connects to the same neuron with string -4, which means that like when I activate this neuron, I tend to activate this this other neuron in the middle layer, but if I activate this neuron, then I tend to deactivate this neuron in the middle layer. So when you propagate the signal, you can this kind of connection leads to a very simple linear algebraic computation of what's called the pre-activation. So the pre-activation is just the obvious linear combination of the neurons in the previous layer, where the weights of the linear combination come from these weight values of a connection. So here it would be 1 times 2 plus -4 times -2, which equals 10. Okay, so far just linear algebra, but the distinguishing feature of neural networks compared to just plain linear algebra is the presence of activation functions, which are nonlinear functions that takes a pre-activation, again, which is computed from linear algebra, and then maps it to some other real value. But the point is that this function is a nonlinear function, and so you get so like a typical nonlinear function looks like this. It's like a sigmoidal function, and so you get activation. And the activation is what gets propagated into the next layer using linear algebra, and so on and so forth.
So in some sense, you're smoothing out extreme values with the sigmoid function.
Yeah, with the sigmoid function, yes. Yeah, you're kind of soft capping.
That's is there a cost to that ever? I guess it's not so clear.
Is what?
Is there a cost to that?
Yes. So in fact, like nowadays, usually people don't use sigmoid because so in the forward pass is good. You're capping the extreme values, But when so I'll talk about this in a second. When you try to train it, you need to compute the gradient. And so you need to take the derivative of this function. And the problem with that is that, like if you look at the derivative, this essentially is not, it's like a bell curve, like a, Gaussian curve, where like, if you go too far left or go too far right, then the gradient is 0. So you have no signal to like improve your network. So people tend not to use it these days. Okay, so let's keep moving on. This is just a refresher of basic concepts. So
sorry, what's the output? Did you say that the output is a sum of?
yeah, so the same kind of behavior here. So for example, this output neuron is a linear combination of these deactivations in this layer, where the linear combination, the weights of the linear combination is given by the strength of let me see.
No, but I mean, like, is there an activation function again?
Oh, at the output? Yeah, I mean, in some sense there is. Yeah, let's just say it is. It's I mean, essentially there is, but like depends on how you look at it. You might, when you implement it, you might want to put one or not in the output. But it's not a very strict. Okay. Okay, so something that will become very important here is the notion of width. Width is just the number of neurons in a given hidden layer. So here, for example, this hidden layer, there are 4 neurons in here. Okay, so the width is 4. So I want to distinguish this from the input dimension or the output dimension. So these are, this is input dimension 3, output dimension 2. But width is kind of like something that you will not be able to see outside of the neural network. So like, for example, you will not be able to see what the width of my brain is, because I only interact with you, through voice and gestures and so on and so forth. So you will not be able to peek into my head, what is my width. So this is a notion for the like hidden parts of the neural network. And then another notion of model size here is the depth, which is number of layers. So here there's one hidden layer, but you can imagine there are like 2 or 3, just inserted into the middle. Okay, so width and depth are very common notions of model scale, model size. Okay, so any questions or?
So typically, when we think of these billions of parameters models, what's the width and what's the depth?
Width is on the order of like 10,000, let's say, and then with depth is like on the order of like 100.
100.
Yeah, like I mean low, yeah, usually lower than 100. Okay, so the way we so this describes how the neural network, processes information. But you need to train it to be able to process anything meaningfully. So the training process just means, like learning patterns from data. And the way you do it is very, very simple. It's, like very classical algorithm called gradient descent. So the point of gradient descent is, for example, if you have like, if you have a landscape, like a landscape like this, f of x, where x is the x-axis and the y-axis, and you can start somewhere on this in this value, then gradient descent just means if you look around your surroundings and identify the direction of the greatest descent into this valley, and then you take that step. And so the objective is you want to decrease the number of decrease the objective value as quickly as possible. So the objective value, in the case of neural network, is kind of like the number of mistakes you make on like image classification, right? Like you want to decrease the number of times you misclassify a dog as a cat. So this kind of thing. So in this picture of gradient descent, the x-axis is the weight and bias space. So the weight, again, the weight is like these numbers of the connection. So this is the weight of it. And the y-axis is like the number of errors you make. So you want to decrease the errors by moving in the weight space. You want to adjust the connections between neighboring layers so that the network performs very well. So these weights I did not talk about biases, but it's very similar concept. These are called parameters of neural network.
Activation function in the internal layer. So that's fixed before that. The function is fixed.
Yeah,
The weights
yeah.
are what you're trying to do.
Yeah, usually it's fixed as like if a sigmoid function or something else, a Revit function. Yeah, you do not train it. Do not train it. Yeah. Okay.
But do you make a difference?
Yes, the activation functions can make a difference in the performance.
For example, for like, I mean, depending on the domain,
Depending on what
domain,
domain, yeah.
does activation, like, can it be that one class of activation functions works well in a particular domain?
Yeah.
Fails in another?
Yeah, so you can, I think most commonly, I guess, so in the interior of the neural network, I think typically nowadays people use something like this. Something like this. So the sigmoid is like this. This is sigmoid. Something else called the ReLU is like like this. So it's like linear on the right hand side, and then like flat on 0 on the left side. So that doesn't change too much between domains. What does change a lot is you can think of like an activation function on the output neuron. But it's more like kind of the objective function, like the loss function you use. Like so sometimes so I guess coming back to this picture, right? Like so I say the number of mistakes here, which is a discrete number, is an integer, like in some sense. But I mean that's very hard to optimize. Like discrete optimization is very difficult problem. So typically people use a proxy. They don't actually optimize the number of mistakes directly. They optimize like in some sense like smooth interpolation or like some proxy of it. So like for example, if you can like map the correct label to a vector, like a real vector, and then you just like take the L2 loss. So the L2 loss is like a square norm of difference between the network output and the label. Okay. So that's a very typical and classical way to proxy for number of mistakes, because if this L2 norm equals to 0, then you will predict exactly the label, right? So it's aligned with what we want. But there can be other notions. I mean, like obviously you can also do L1 instead of L2, so like you can just change the P and LP. There's also other things that use more like information theoretical point of view when you have multiple classes. So you can essentially take the KL divergence of the prediction of the network and label. So I won't go into detail, but like, so there are like a lot of different ways you can think about this. And oftentimes when you change the name, it's very fruitful to change the objective function. So this loss function, right? Like you can change from L2 to cross entropy, like this KL divergence, for example. Okay, so hopefully that answers it. Okay, so yeah, so in your networks, when you do gradient descent, you need to compute the gradient of the error function. So the error function here is essentially the loss function I mentioned. It could be like L2, this L2 function, it could be this KL divergence. So these are smooth functions. So you can like compute the gradient of the smooth function against the parameters. And then that identifies like the right perturbation of your weights, the connection of the neural network that you should perturb the weights by, so that you do better in the next step. Okay, so then you iterate. So it looks like this. You're just like hopping down a slope until you reach the bottom, and then the bottom of the slope just indicates that you're at a local minimum, where like no matter how you perturb the weights, you will not improve your objective. Okay, so this is the basic picture of gradient descent, and if you like this, so there's a lot of very large literature of this classical algorithm, studying this classical algorithm of gradient descent. This dates back to centuries, to like Cauchy or Euler, or I don't remember the exact origin. And you can see that if you like take sufficiently small steps, in continuous time, for example, then yeah, like in this picture, at least you're definitely going to converge to that. But in practice, you want to take very large steps and like take few steps because number step is the computation cost. The more steps you take, the more costly it is. So you want to minimize the number of steps you take. So you want to take large steps. So it's of very high importance in practice to understand, what should we be learning on this, which is just how large of a step you take. Okay. And secondly, it also is often underlooked, but it's also very, very important in practice to understand what is the right starting. Okay. I mean, so here, like on a one-dimensional picture like this, you can just pick a random point like here. But when you have a very high dimensional picture, where should you start? So usually people sample all the ways randomly at initialization. Okay. And then they start, optimizing it and going down the hill. But for example, there's a very basic question of like, what if you randomly sample, what is the variance or standard deviation of the sample, right? So if your weights if you like sample the weights to be on a very, very large scale, like a very large standard deviation, then you can be very bad because like you can't have like explosive behavior in the neural network where like, like when you propagate, over multiple layers, the activation values become very, very large because the weights are very large in the translation. And conversely, when like, if you use a very small standard deviation, everything is near the origin. But that's not, often that's not like that's like very suboptimal point. And it's also like a saddle point where you don't get any signal on how you improve. So, so this is a very complicated consideration, but again, in short, you want to know in practice, you want to know how you should understand and scale two things, initialization and learning rate at the very least. And this can be, per layer. So you remember like there are multiple layers in your network. So we can have like a different learning rate, different initialization for every layer. Okay? And this turns out to be very important. Okay. So that was a brief review of deep learning. Anybody has questions?
So width and depth are also hyperparameters.
They are, yeah, like a traditional notion of hyperparameters. Here, I'm just going to focus on just these. So, I mean, so the interesting thing about these two kinds of hyperparameters that when you change them, you don't change the cost of your computation. I mean, just some numerical change. When you change width and depth, you change the cost, and that's a more complicated discussion.
I mean, when you choose the initial architecture, how do you sort of estimate the depth and the size, the width that you say?
Yeah, it's a very empirical process. It's kind of like an art in some sense. But oftentimes, when you have a new architecture, you're kind of you're modifying it from previously known architecture. So so there's always a history of a year ago, like people did this. Now I'm doing this. So like I'm basing some design choices on what is known to be good in the previous popular architecture. And so there's always when people design these things, they always have in mind the history of how the architectures evolved over time, and then they base their design decisions, like kind of taking the good parts of the previous design decisions in previous networks. So again, there's no, in general, there's no exact science here, but yeah. So.
Are there some approximate methods of just exploring the cost function space, the cost function plane, in a computationally cheap manner, like just approximating it to design?
Like, well, what do you mean by exploring the space?
So that we are able to understand the learning rates, like what sort of learning rates and initialization should we choose?
Yeah, I mean, definitely on point models, you can on this one-dimensional case, of course, you can map out the entire thing. The problem is that in higher dimensional, well, first of all, when it's high dimension, you don't even know how to visualize it, like how to even store, efficiently the data that will represent the landscape. So it's hard to visualize, hard to understand a high dimensional picture. And three, I mean, it just gets very, very expensive to do it. So I mean, as we'll see, I mean, in some sense, like the whole point of today is that there are tractable ways to understand this high dimensional picture. But it's not, you have to think very carefully, and it's a subtle thing. Does that make sense? So in short, you can try to brute force the high dimensional picture, but it just is, for all these reasons, it's very hard to do.
So we can just plot, like we can vary these initialization and learning rates and plot them on weights and biases sort of a thing and understand which works better. So
Yeah, so for example, that's a more tractable way of doing it. Yeah, and then as we'll see, if you do some more careful analysis, you can do even better.
Typical applications, if you try different starting points, just in case you end up with a better local maximum or something, and you just have one.
Yeah, I mean, like definitely people, like the initialization scale is a very common hyperparameter, and like pretty good practitioners will have a very good intuitive sense of like what is like a right scale of things. And oftentimes, yeah, initialization can make a huge difference in performance. Okay. All right, so that was a brief refresher. Now the main topic of today. Okay, so suppose you travel back in time to 1969, and Kennedy said, "Let's go to the moon" in the U.S. But Stalin also said, "Oh, we're going to go to the moon too." But the problem is that when you travel back in time, your time machine misfunctioned, and you got rid of Newton in your timeline. So there's no Newton in your timeline. So your mission. So Stalin noticed that you're a time traveler, so he's like, come, like make me a rocket. And so your mission is to make a rocket with the astronauts in the rocket, so that you can land on the moon. Okay, so that's you had to do it before the dirty Americans. And but again, the problem in your timeline is that there's no Newton's law. Nobody knows what Newton's law is, but you somehow remember from grade school that it's like something like F equals m1 times m2 divided by r squared or something like that. But luckily you remember the form, but you don't remember the constant, the gravitational constant. But Stalin's like, it's okay, comrade. We have a lot of manpower. You can use as much manpower, as much money as you want. So your strategy is to just make lots of rockets and shoot them at the moon until one of them lands. So first you guess that the gravitational constant is 6. So you try to shoot it, and unfortunately you missed, and everybody on the rocket dies. Okay, it's okay. And Stalin says, it's okay. Try the next one. So you plug in 7 instead of 6, and then you miss again. Okay, and then but because the USSR has a lot of people, you just keep training astronauts and shooting at the moon, and eventually got it very close. So after a lot of blood and iron, you got the constant down to 6.674. Okay, so that was good enough to land on the moon. Okay, so you get a round of applause from Stalin.
You're missing the 10 to the power minus 11.
Yeah, that's a huge mistake. But here I'm using the custom units so that you can get rid of it. Okay, so obviously we have Newton's law in our timeline, so this is a very stupid way to do things. If Newton was in the timeline, then he would just say, gravitation is universal. The constant gets measured on Earth. You don't need to try and error and shoot rockets at the moon, thinking the constant only applies to the moon. So this is the story of trying to create a space program without Newton. So it sounds very stupid, but really, today something similar happens with training large language models. So with large language models, instead of trying to shoot a rocket to the moon, you just train a very intelligent language model, like an agent, not going to converse with you. And instead of so this is kind of suppose you want to train GPT 9000. It's a huge model. So shooting the rocket, each trial of the rocket is like a training run of the neural network. So you try to yeah, so you try to like train the neural network on like the internet, for example, so that you will like do really well and be very intelligent. But the problem is that this is not a very cheap process. It's not like you can just train one in an hour and then you can just train like 1,000 of them in a day, right? So the process of like so the process of shooting a rocket to the moon can take, I guess, like like days or months. For this large model training, it can take months. So like, I mean, this is a kind of wide range, but definitely it's on the order of months, like 3 to 12 months, give or take.
Sorry, when you say you train multiple large models, what does that mean? Like, what are you wearing each time? The training data is the same, I guess, right?
So yeah, so let me continue. So so instead of varying gravitational constants in your rocket shots, you vary the hyperparameter. So the learning rate initialization that I talked about, for example, right? So like I said, these things can be very sensitive, and I mean, ideally they're not sensitive, but they can be sensitive. And if you choose the wrong values, you can just your model can just blow up and die in the middle of training, like after a month. Like then it's like, ah man, I wasted like $10 million. So it's very important to set these constants correctly, these hyperparameters. So you can see that this is it's a very costly problem, and really what I mean, more or less what practitioners do is kind of like just try like a lot of different options and see which one sticks in some sense. It's a very like trial and error kind of thing. Okay, so it turns out that the point of this work is that it turns out like there's also kind of Newton's law for a large model training in this sense of the analogy. And the analogy is that like instead of gravitation is universal, the hyperparameters are universal in the sense that you can measure the optimal hyperparameters on a small model and obtain the right a good estimate of what the numbers are for a large model. Right. So this is analogous. You can measure gravitation on Earth and you can get a pretty reasonable estimate of gravitation will look like elsewhere. Wherever Einstein's relativity doesn't is not needed. Like when we're not traveling in your speed of light, then Newton's law is pretty accurate. Okay, so what is this Newton's law for neural networks? So is this thing called maximal update parameterization, briefly UP. So I'll talk about the exact details in a second, but I just want to know, first of all, it's already out there. You can just use it today. You actually use deep learning, like Pippin install UP, you use PyTorch, and conceptually, it's just a principal way of scaling the initialization and learning rate with the model, backed by some beautiful mathematics that I'll talk about later if I have enough time. So okay, so this is a table that shows what UP is. Don't worry about what it says. The point is just that like it's a very simple thing at the end of the day. It's kind of like in Newton's law, it says the force is equal to constant times m1 m2 over r squared. Okay, so let me discuss instead first how what exactly is the property that we like about UP. So just to put things on the page very clearly, it has these two properties that we call hyperparameter stability and larger is better. So to understand these notions, it helps to first look at a negative example, how things are done currently. So the standard computation is what people are doing currently for the most part, like people in PyTorch. And so you can do the following experiment. So you can take your favorite model and you can through rockets, right? Just like try many different hyperparameters, like many different learning rates, many different initialization scales, and you can train a bunch of them and then see like how they perform as a function of the hyperparameter. So, so you can plot the result, you would get something like this. So you will tell you, okay, this region of the hyperparameter is optimal. Okay, indicated by this vertical dash line. So far, this is very, a very common picture, like nothing non-trivial is happening. But if you try to repeat this experiment as you scale the model size, so for example, scaling the width, making the width larger, and repeat the experiment, you see this set of curves. And you can notice that like the optimal regions of the hyperparameters are shifting as you make the model larger, right? So in some sense, it's not like predicting the the large neural network's optimal hyperparameter from a small one is not the right thing to do. And furthermore, like you see that if you, for example, fix a hyperparameter and you increase the model size. So like, for example, if you were to just like look at this vertical line here and see where it intersects all the curves, then you see that, as you increase the model size, you get better performance, but then you start dropping. Right, so it's not, the performance is not monotonic in the hyperparameter, in the scale, in the width of the network. So this violates larger learning. Okay, so again, like these, hopefully this gives you a sense of what counts as negative examples of these properties. Now we can look at muP, and you see that if you redo the same experiment, you can see that optimal hyperparameters are stable, and you always gain some performance when you increase the model size. So this is a positive example of hyperparameter stability in larger data.
In the left-hand picture, this is certain equals to overfitting, or it's because the loss function is not really nice.
So I'm just finding the training loss here. It's training performance. So it's not even talking about generalization. It's even simpler problem. Yeah. So again, like the hyperparameters here can be learning rate of generalization and so on. So this is a cartoon to show the concept very clearly, but in reality, it's very similar. So, for example, here I'm training like a transformer, which is a very state-of-the-art model. Like GPT is transformer, for example. On some real data sets trained by some state-of-the-art optimizer. And on the left side, you can see that like the curves are shifting to the left, right? As you increase the model size, which is indicated by darker and darker colors. So the optimal learning rate started here for the smallest model and ended up here for the largest model. You can see that the absolute optimal performance on each curve is not exactly monotonic. It goes like this. So it decreases, the loss decreases, so that's better, and then it starts increasing again. Okay, so it's not monotonic. And finally, if you like, for example, take the best learning rate on the smallest model, which is like this vertical line right here, and then you try to use it for the largest model, which is this dark curve here, right? So then like obviously you're going to do much worse than just using small model. Right, so this is, yeah. So this is again, like just like a real instantiation of this this phenomenon you see on the left. And whereas if you use muP, then you see that like the optimal hyperparameters are stable, the curves are not crossing, and you always get like darker curves like beneath the lighter curves, right? So this is everything. Okay.
So then comparing standard practice with your work, like so what is the difference in terms of the way we start off with the hyperparameters? Here we are just changing the learning rate and the other parameters are fixed, right?
Yeah.
muP.
So here in this experiment, we're just fixing every other hyperparameter except for the learning rate. Okay. Now like I haven't defined what muP actually is yet. Remember I showed you a table in the beginning, but I did not explain it. So we'll come back to that in a second. But like muP essentially will change the initialization and learning rate for the output layer and for the input layers and biases, and the learning rate for the middle layers. So you will change a lot of things, I guess. Like how you scale those hyperparameters. And so that's why like it's a bit complicated, even though it can be summarized very simply. So we'll come back and discuss what it means later.
Just to get a high level picture.
Yeah.
So, so what maybe should be doing is it's defining what your hyperparameters are in a slightly different way. In some sense that incorporates the model size.
Yes.
Such that under this, in some sense, the shifted basis or whatever these
Yes.
curves line up.
Yes,
Right.
that's right. It's kind of like a width dependent change of basis.
Okay.
So that you have the property that, the optimal hyperparameters are approximately invariant. Okay. As you become larger.
So in this framework, you can use smaller model, find the optimal learning rate and use that larger model.
Yeah, that's exactly right. So this is what you just said is called the muTransfer. So again, instead of directly trying like shoot rockets with a large neural network, which will cost a lot of resources. So like so the top is kind of shooting rockets like this. You shrink the model, you tune the model you can tune it very aggressively and obtain a really good set of hyperparameters. And then you can just transfer or just copy the large neural network by scaling it using. Okay, so the scaling relation between small model hyperparameter and large model hyperparameters are given by this kind of set of scaling rules. And this is kind of like Newton's gravitation law that says if you test if you like obtain gravitational constant on Earth, you apply on the moon as well. Okay, so any other questions?
So this is for a class of neural networks where small and large are in the same class, but in what sense do we have to redo this again when the class changes?
Yeah. So here we're just changing the width of the neural network. If you remember the picture in the beginning, the width is the number of neurons each layer, but you're keeping the overall structure of the neural network the same. So when you change the architecture, for example, like when you add attention or convolution, and then like the optimal hyperparameters potentially will change. So you need to redo. So at least like a priori you should redo the tuning. But a lot of times if you make a very small modification, the optimal hyperparameters might not change that much. So you can kind of get away with just being very lazy and not doing it. But we'll see as like right now, I'll show you that in fact the cost of like tuning these small network is negligible. The cost of tuning is negligible, so you can just redo it. Like, it doesn't really cost.
How does it scale? The cost?
Okay, yeah, exactly. So that's the next part. So we did a lot of experiments to validate all of these things I said. So this is just a representation of the wide variety of models and scale of models that we tested. So like this is a very small model, NLP and Super 10, and the 6.7 billion parameter model of GPT-3. This is a very large model, at least on this scale. So when you look at all of these results, and you can find the details in the paper, you'll find two patterns. One is that the improvement due to muTransfer. So if you take an existing model, which is hand tuned by a lot of really good practitioners, and you redo the tuning, like optimize for the hyperparameters using UP. So you shrink the model and tune it very well, and then you just copy the hyperparameters to the large model. So when you do this, you find that you always improve your performance compared to the baseline, the hand-tuned baseline. And also, furthermore, that the improvement due to muTransfer increases as you increase the model scale. Okay, so if you think about it for a second, this is a slightly counterintuitive usually, because the counterintuitive part is, in practice, in any kind of practical field, if you like have a really shitty system, it's not really functioning. It's very easy to improve the system. But if you have a really well-functioning system, then it's much harder to improve it because there's just less avenue to improve it. So usually in deep learning, for example, you can try to propose new techniques to improve some model. then usually you'll find that, like a 50% accurate model improves by like, 10%, so you get 60%. But is you on a 90% accurate model, it's very hard to improve 10% to get 100%. Like that last 10% from 90% to 100% is much harder to attain than from 50% to 60%, right? So this is like very common sense, but here you have the opposite. Like, so here, like for the better models, the larger models, you're improving more than for the smaller model. Okay, so it's kind of very counterintuitive.
Just wanted to ask, so all of these models that are here, so how is their architecture similar to each other? Like, how do they fall in one family?
Yeah. So so this is MLP is just kind of like what I in the very beginning, the baby picture of a neural network, just like 3-4 layers. Okay, just fully connected. The transformer is just like a state-of-the-art architecture for like language modeling, like like GPT is a transformer. So the architecture for this, and this are very similar. Not exactly, but like more or less about the same. Like the overall shape is about the same.
GPT-3 uses transformers, right?
Yes. Yeah, the T stands for transformers.
Yeah. So how many transformers do they typically use? The GPT-3, like that's the
Yeah,
type.
how many layers were?
So do they use transformer units or transformers become more complicated for as we increase the volume?
It's essentially the same structure, just the number. I mean, so number of neurons, which is the width of the model, and the depth of the model increases. And I guess there's some like potential improvements. Like there's something called mixture expert, which is which I won't explain, but it's like some additional modules inside of the transformer that you can add. But yeah, the transformer, like the point of transformer is that there's a attention mechanism, and that is still like that's always in there.
So it's the same transformer but expanded, like adding.
Yeah, in some sense, yeah.
So I have a ridiculous proposal. So the thing is that so you're saying there exists this function mu that can instruct it. So why don't you just start with a few small model, learn the function mu, and then instruct?
Yeah, this is essentially what people do before all this work. I mean, people are not. I mean, people are. Not everybody's a good mathematician, but people are not stupid. Right? So, like, you would try to tune multiple networks of different sizes. So, like maybe like you tune some small models and you tune some large models, and then like you some in between, and then you look at what the, for example, optimal learning rate is, right, for each of them. It can just like fit a curve, right? That's like the simplest case of what you're talking about. And you can try to extrapolate, like, when I train this large model, like what the number looks like. So this turns out to be like pretty suboptimal when you get larger and larger. I mean, there are multiple reasons. One is that you can only do this for like, a small number of hyperparameters. Like learning rate is like the most typical one. But in some sense, the true picture is not this one-dimensional picture of just a learning rate. The true picture is like a very high dimensional space of like learning rate initialization for every layer. You can have momentum or whatever. So it's a very high dimensional picture where all these hyperparameters form this large space. Okay. And what happens is that like when you just look at learning rate, you're implicitly fixing the other hyperparameters. And the way you're fixing them actually is wrong. In the sense that like if you look at this one-dimensional space in this high-dimensional picture, like this, as you increase width, like this one-dimensional space gets farther and farther away from the true optimum. Okay, so even if you optimize in this one-dimensional space, you can extrapolate what the optimal value here is. It's actually very far away from the true optimum in the whole space. So that's, I mean, this partly the reason why you see this improvement is that we're picking like the total, the absolute minimum performance or loss, I guess, the absolute optimal loss. Whereas if you try to extrapolate naively, you're kind of like, picking the best out of one-dimensional subspace, and the kind of like you saw earlier. So on the left side, this is essentially what's happening. So you pick the one-dimensional space in this high-dimensional picture. And even if you optimize in this one-dimensional space, as you increase the model, it's possible that the best performance on this one-dimensional subspace actually decreases as you increase model size. right? Whereas like on the true optimum, performance should never decrease as you increase model size.
Isn't the dimension of the hyperparameter space increasing as the model size increases?
So that's not that's kind of the whole point of hyperparameters. The hyperparameters, the dimension of hyperparameter is always fixed as you increase the size of the model. The dimension of the parameters will increase as you change the size. So that's like the number of connections between neurons, but that will always change with model size. But the hyperparameter, the point of the hyperparameter is that it does not change with model size. So we can like kind of use the same hyperparameters for models of a large range of sizes.
Because initialization is not just the weight initialization of the edges. Because if you have more edges, then you have a higher dimension space.
Yeah, so what I mean by initialization here is if you recall, I said, a lot of time, like, essentially everybody, when they initialize, they randomly sample the weights. So what should be the standard deviation of the sample? So that's just the scale. Okay, any other questions?
Yeah, initially, so people used to do this since learning to learn, right? Like meta learning and mammal kind of thing, yeah. So is it like a new way of replacing mammals with this?
Yeah, I mean, I guess you can. I think, I gave a talk on this at meta learning workshop. But I mean, I think the point is that I think meta learning will be pretty hard. I mean, meta learning in some sense, in the end, is still like interpolating in some sense, and you're interpolating just like on distribution of tasks instead of on a specific task. So like this really requires extrapolating, and yeah, neural networks are kind of somewhat bad at extrapolating. So I mean, as you see, like if you do the math correctly, then everything just works. So you don't even need to do any computation heavy stuff.
Just a naive question, we fix the hyperparameters to increase the model size. And we train it. How does the computation effort increase? Is it exponential the size or is it?
Yeah, you mean like the tuning cost or the training cost?
The training cost.
Training, right? It's like roughly proportional to the. Well, I mean, yeah. If you fix the training time, then the cost is proportional to the models. Training costs, the loss.
It's linear in model size.
Mhm.
It's not exponential.
No. Yeah. Okay, so anyway, coming back to this picture here. Again, the improvement due to transfer increases the model size. This is counterintuitive. Because usually you expect the other direction, we would expect the improvement to decrease.
Just want to get a sense of scale. So that one has about 6.7 billion parameters. Like how many parameters does Wikitext2 have? So it's just a separate.
Yeah, like I say, like the MLP on Cypher 10 is like, let's say, I think with 10,000 squared. I guess like at most 100 million parameters. It can be yeah, but it should be less than that. Maybe like more like 10 million. Like 10 to 100 million. These are largest you use on this scale.
But as we increase the number of parameters, the number of neurons, for example, not in the transformer, the number of parameters such as weights would increase exponentially. So shouldn't the training cost increase exponentially?
It's not exponential. It's quadratic. It's quadratic.
It depends on the width also. Okay? So it will be. So there will be a WI for each of the neurons the next level.
Width is fixed,
And that will just
the depth is fixed.
If you fix depth, the increasing width of the neural network will increase the parameter count and most quadratically. If you increase depth, it just increases linearly in depth. So it's quadratic and width and linear. I mean, like, I guess maybe you're thinking of number path or something.
Yeah,
Number path
exactly.
is sure. A number path is like something like width to the L depth power. But that's not what you actually train. You train only like the actual parameter count is quadratic and width, linear and depth.
Whatever is inside has only W times D many wires. And each wire has a number.
Okay, so, okay, so coming back to this trend, essentially what this is saying, even though it's counterintuitive, like the reason you see this trend is that like, kind of like how I answered your question, like people didn't know how to tune hyperparameters, so like they're kind of tuning in a like subspace that's farther and farther away from the true optimum of the loss landscape. So just by doing the right math, you can like identify like, the right region that you should be tuning in. And so in some sense, like the hand tuning of hyperparameters from humans with no math is just gets bad and it gets worse and worse with model size. So that's essentially what that is saying. And then coming back to your question, if you look at the total tuning cost, the tuning cost is like the if you look at all the small models and try to aggressively tune the models, do the small models, it's kind of like shooting rockets, you know, if you recall, but you're shooting very small like toy rockets. So you can shoot like 1 million of them if you want, and then try to get like a very good estimate of the right hyperparameters. So even if you shoot like a lot of rockets, small rockets, the total tuning cost combined is only a very small fraction of the training cost. And like the trend is as the final model size increases, this fractional cost actually decreases to 0. I mean, the reason here is I mean, as we'll see by time, essentially the theory here guarantees that if you tune the model on a sufficiently large network, which doesn't have to be actually that large, then the hyperparameters obtained should be optimal for arbitrary large hyperparameters. Okay, so again, so it's like a one-time cost in some sense. You have a fixed cost on tuning on fixed size in your network, and then the optimal hyperparameters that you obtain will be able to will essentially maintain its optimality for arbitrary large.
So you say what are training cost and training cost?
So like, you know, so like in the rocket analogy, right? So like you don't, it's very costly to shoot a rocket to the moon. So you want to avoid this. You only do it once. You only do it once after you figure out the gravitational constant by getting it from like shooting a lot of small rockets. So you can make a lot of
Tuning cost again a hyperparameter.
yeah, so you can like, you know, try to like, you know, here you can try to train like, you know, 100 different hyperparameters. So learning rate 1, -3, learning rate 1, learning rate 100, you know, so on and so forth. And then you can just try on small models, and you can try a lot, and you get one you're happy with, and then you copy that to the larger model, and you train the large model once. So the total cost of like, you know, say like you train 100 small neural networks, the total cost of that is a very small fraction of the total cost of the large.
So you mentioned standard deviation of the weight to the hyperparameter, but then you're looking at a randomized initialization. So even there's some sort of concentration, because otherwise it seems like there is concentration.
Yeah, there is concentration. I mean, you'll see some fluctuation in performance when you randomly like when you initialize using different random seeds. But more or less, like you can see, yeah, the concentration. So like more or less, the performance will be very similar if you fix the standard deviation, but you randomly sample. But if you change the standard deviation, oftentimes you see a very different learning curve, very different performance. Okay, so again, so like the trend here essentially suggests that muP is essentially a free lunch. You're on large models, you're essentially for no cost, you're improving the performance, like, you know, by massive. So so this is like one of the rare I guess occasions where practitioners just did not have the right intuition for the right thing, and doing the right mathematics really influenced the correct thing to do for large scale models. And so as a concrete example, like if you look at the GDP3 example, the model is 6.7 billion parameters. You shrink the width and you get a 40 million parameter model. And when you like do all these things, like for a cost of 7% of the final training cost, you get a model that's effectively double the size. So like the 6.7 billion parameter model is approximately as good as the original GPT-3 13 billion parameter model. Okay, so but of course you expect the improvement to get even larger as you go to large scales. Okay, so how am I doing my time? Seems like I'm running out.
Yeah, half an hour.
Oh, I have an hour? Okay, all right. Sounds good. So I actually told you what Maxwell update is. So that's the plan next. But anyway, like maybe like if you guys have any other questions, you can ask now.
One distribution for all the edges in the network, if we have like.
Yeah, very good question. So it turns out you want different distributions, a different standard deviation for different parts of the. Okay, so. Okay, so before I actually move on to the neural network part, let's just I look at some like toy examples that doesn't even have to do with networks. So consider the following scenario. I'm going to sample numbers W1 to Wn from a Gaussian distribution with mean 0 and standard deviation 1. And then let me compute the sum of these numbers, okay, multiplied by C. And so let's set this to be a Zn of C. So C is like, yeah, a number, okay, and Zn is this number times sum of these renewable numbers. And then I have like kind of like a loss function or a landscape like this, okay. F of z equals z to the fourth minus 6z squared. So it will just look like this. I mean, don't worry about this equation. And the toy problem is I want to like minimize this function, the expected value of this function, when I feed z and c into f. Okay. So I want to find the optimal c here, so that will minimize this expectation. Okay. So the toy question is, how does C star of n scale with n? That make sense? So what's it?
1 by root n.
1 over root n, right? Exactly. So yeah, do you want to talk about the reason?
We wanted to be the same distribution.
Yeah, exactly. So I mean, yeah, if you scale C like 1 over square root n, then you know the sum essentially has the same distribution. No matter what the n is. So like it's obvious like you want to minimize this function, which is fixed with n, then like the optimal should scale like 1 over square root. Right? So pictorially you can represent this like the following, where you can plot C star on the x-axis and then n on the y-axis, but all in the log scale. Then 1 over square root of n, like the way you scale C star would you know move like this. Right? Cool. So great, you get plus 10 points. Great. So now the second problem. So I have now kind of W1 Wn again, but now I'm sampling from Gaussian with mean 1 and variance
1 by n.
very good. So I mean it turns out to be roughly square root of 3 over n, but anyway, the point is scaled like 1 over n. You want to explain what the reasoning is?
The means going to dominate, right?
Yes, yeah, so exactly. So here the point is that the means will dominate in some just many copies, whereas like the original like this the fluctuation will be like scale like square root of n, but the mean will scale like n, or the mean will scale like n. So you want to divide by n instead. So this is a law of large number behavior. So again, if you plot it on this picture here, you get 1 over n, right? So like you will move like this. So you will decrease faster as you increase n than 1 over square root of n. Okay, so final question. So now I have two set of numbers, I and vi. So one is from normal 0, 1 and one from normal 1, 1. And then Zn C is max of essentially these two problems. C1 times the sum and C2 times the sum of vi. Okay, so So what is so there are now two numbers. So C is C1 and C2 is a two-dimensional problem. So how should C1 and C2 scale? With n.
Well, can you explain say what it means?
Yes. So essentially just combine the answers. Right. I mean, it's the same. The reasoning is essentially the same. You want to. I mean, even though you're taking max here, you want like what's inside the max to be kind of invariant with n. Right. So C star would be just yeah. So C1 will be 1 over root n, and C2 will be 1 over n. Okay, so the point of this toy problem is to demonstrate something like the main intuition and insight here into the behavior of a large neural network. So the analogy here is that W1 and Wn are kind of like weights, the connection, in the beginning picture of the neural network, and the n number, the number of W's here is roughly like the width of the neural network. So kind of like what you're asking, like when the width is large, you get some kind of self-averaging behavior, not like what's happening here. And then here in the final example, we have Wi and Vi, and these represent the weights from different parts of the neural network. Okay. Okay, so now with this toy problem in mind, let's look at a real example. So here, this is the formula of a 3-layer neural network, and yeah, so there are 3 sets of weights. So maybe just to connect with the beginning picture. So when you remember I had like maybe I'll just go to the beginning. So if you remember this picture, right, I have like a 1 hidden layer and then like an input layer and output layer. So this is called a 1 hidden neural network. 1 hidden layer neural network with 2 sets of weights. Okay, so now in this example, I insert another hidden layer. So now there are 3 sets of weights. Okay, and I mean, like you can kind of abstract what I said here to like a linear algebraic formulation, and the resulting formula you get is essentially something like this. Okay, so given input xi f, the function, the neural network function would multiply it by some matrix which represents the weights of the first layer, and then the resulting number you feed it through some nonlinear function feed and repeat, so on and so forth. Okay, and just to know, if you haven't seen deep learning literature before, it can be the sigmoid function, so it's a scalar function from R to R, but when you apply it to a vector quantity, it's applied entry-wise. Okay. Okay, so hopefully this makes sense. You can ignore the biases if you don't know what it means. But yeah, so if you look at standard translation, the way this works is that in translation, you sample W1 from something like a Gaussian with 0 mean of variance whenever d in, where d in is the data dimension, the like number of neurons in the input layer. And W2 and 3, the middle and the output layer, will have variance 1 over n, where n is the width of the neural network. So roughly speaking, like each matrix represents like the connection between one layer of neurons to the next layer of neurons, and the standard translation just samples the weight entries with variance that's 1 over the number of neurons going into the next layer, the number of input neurons of that connection. Okay, and then the bias is set to be 0. Learning rate is 1 global learning rate called eta. Okay. Okay, so if you take this description and do those experiments you've seen before, where you like vary n, where n goes from 256 to 8,000, then you see this set of pictures where the curves are intersecting everywhere. If you take the best learning rate for the smallest model and use it on the large model, then you're gonna do far worse than the small model itself. So this is a very undesirable picture.
Although the flatness to learning rate near the optimal region is useful, right?
Yeah, it is, you definitely would like to have flatness in general, because then it means I can make small mistakes and it doesn't matter. Yeah, I mean, but this is kind of like an orthogonal property to UP. Like sometimes you have flatness, like other times in the curves you saw in the beginning, you don't have flatness. Okay, so now let's try to see how we try to fix this situation. So you have three modifications here. So one is the downscaling of alpha layer variance, so 1/n to 1/n squared. Another one is the downscaling of the learning rate from eta to eta inverse. And then finally, we have upscaling of the learning rate and the input layer and the biases. Okay, so this definitely looks like a random collection of modifications. If you've never seen this before, and we'll explain in a second what's going on here.
But one of the velocity kind of learning rates are always decreasing, the noise is always decreasing as you move forward.
Yeah,
Is that kind of stuff?
yeah, yeah. So in particular, like learning rate, for example, it was invariant to width before, now it's decreasing, inversely proportional. Right, so yeah.
So that will continue even if you have more layers,
Yes, yeah, so this is kind of like a well, I'll say that like if you add a layer, then I don't actually say anything about how you scale the number layers. This is more about like when you increase the width. So I guess like naively you would want to retune your hyperparameters if you increase the depth. Okay, so anyway, so the point here is that now you see this if you reduce sharing, you see this figure, which is very nice, and the bottom one is stable. Okay, so let me briefly explain why these two modifications make sense. So this will resonate with the, for example, we saw earlier. So the point here is that the output of the network, if you look at this, is a dot product between W3 and its embedding here, and so it's a sum of n things, and so there will be some self-averaging happening here. So first you can, so this is a homework problem, but you can see that like this each entry of the embedding has constant size, which just means that as n goes to infinity, the width goes to infinity, it doesn't blow to infinity, it doesn't shrink to zero. Okay. So with this in mind, you can see that like these modifications ensures that each entry of W3 is 1/n. Okay. So like we can do this calculation to see why this is the case, but let me just kind of keep going and come back later. So again, like the claim is that these two modifications ensure that each entry W3 has size 1/n. So the implication of this is that when you're summing up n things and each of them is size 1/n times 1, then like the sum cannot go up to infinity as you increase n. So this is O of 1. Okay. But finally, the piece of insight here is that when you start to train the neural network, the neural network weights will want to like adjust to other parts of the neural network. That's the whole point of training. You want to adjust, kind of adapt to other parts of the neural network. You want layer 1 to learn as much about layer 2 as possible, so that you can like coordinate in some sense. So they will synchronize. So the final piece of insight is that when you start training, like this sum cannot cancel too much. If they cancel too much, that means that there's too much independence, and like the upper layer doesn't know enough about the middle layer. That means that you're not training. So when you start training, actually like the sum, essentially the mean will dominate, right? Like, and you will get like a large number behavior instead of central limit behavior. So the final conclusion is that the sum will be theta 1, and so that has all kinds of like important implications in terms of the practice of training technologies. And then if you do the same calculation, standard calculation, you see that things blow up, and it's very undesirable. Okay, so this doesn't make sense. I mean, if you're interested, I can like do this calculation of why these modifications imply that W3 has entry size 1.
Is it also clear that because of these adjustments that the size increases, the model accuracy increases?
You can get that calculation, but it's more complicated. So it's a very on toy models you can like do fairly involved calculation to show this issue. Yeah.
So are there more general distributions where you can just sort of figure out what is the right adjustment you need to do? Like, for example, instead of the standard Gaussian, suppose it was an exponential distribution or something. Is there a way in which you can figure out both the right parameterization must involve the one array?
Yeah, I think the distribution here is not like too informative. So first of all, because of like roughly because of universality, like if you replace Gaussian with anything that's not like a Cauchy distribution or something, like as a reasonable tail, then it's gonna get the same behavior when the width is large. Yes, and I mean, like, yeah, I don't think, you know, looking at something else instead of Gaussian is like not much more insightful. So
And also, when the looks of it feels like you don't really care about what the activation functions are, as long as they're in some sense well behaved. So
yeah, that's right. Yeah. So this is the inside is very universal and you can like plug in really any non-linearity and
So I don't understand what this is. LCD is not doing random walk, right? Then why this makes sense?
yeah. So like you mean like why
Yeah, the scaling.
yeah, why the scaling makes sense. So like maybe can you say more like so suppose HED is doing a random walk, then what will be the implication here? I mean,
I don't see like why I mean this equivalent to random walk.
yeah, but like, so are you saying that like somehow here the reasoning seems to depend on actually being a random walk? So where is that coming in? Like, I guess.
So you're using all flats, right?
Okay, yeah, so that doesn't come from actually being a random walk. So for example, like remember like when you randomly initialize a neural network. So initialization, like W3 is literally IID, like the entries are IIDs by construction. And then like the entries of phi are also like roughly IID. So it becomes kind of exactly IID when n goes to infinity, but like not quite so for finite. So I think your question is really about like why. So initialization, I guess it should be kind of rather clear that things are roughly IID at least. I think your question is why when you start to train, like things remain kind of like independent in some sense, like can do some reasoning like this. And this is a very deep question, and there's a kind of deep solution to this, and it's called tensor web. So this is like a framework that I developed over the last few years. And the really counterintuitive part is that because of the way that we do computation in deep learning, it's not arbitrary computation. You're doing like matrix multiplication and coordinate-wise nonlinearities. Like you're always applying nonlinearities entry-wise to vectors. These two properties essentially ensure that like any vector you obtain from this computation are like roughly IID. So one way, maybe one like halfway intuition here is you can observe that when you do this, like just you do matrix multiplication. So when you give a vector, you give a matrix, you multiply them together, and then given nonlinearity and vector, you can apply the nonlinearity entry-wise. So you can observe that any computation formed by this will have the property that any vector you obtain, the entries are exchangeable, like in the probability sense, right? So I mean, like kind of like in this picture. Right, if I permit the neurons and permit the connections, then like things are exchangeable. So that's kind of like, so you can see inside out like the entries are exchangeable, so that's like halfway to IID, I guess. So you can see why there will be a self-averaging behavior. So
intuitively it sounds plausible that if these things growing up is not a good idea. But can someone say something more concrete?
Yeah, so like practically speaking, when you train these large neural networks, you these days you're training using a lower and lower precision for numerical formats. So you can only represent a number in a very small range. The reason people do this is that the cost of training is much lower when you use the format. Like the amount of like circuitry that needs to compute the product of two numbers using this format is much cheaper than for larger. So it's narrow range. So, if the network is blowing up, the output is blowing up like in standard parameterization, then the numbers will go out of range. And you'll get like another number like nans. So in the computation process, you essentially will just your training process will halt or stop because you get nans. So this is very, very undesirable, and like people try to fix it, lots of hacks and stuff like that. But as you can see, there's like a fundamental reason why this would happen in practice if you're using standard computation. Yeah, there's also, if you ignore this issue, there's also like mathematical and algorithmic stability problems. So like if you do some mental calculation and like if, for example, you use like a square loss. So the square loss is a property that if the output is very large, then the gradient of the network is also very large. It's proportional, linearly proportional to the output of the network for sufficiently large network, for sufficiently large output activities. And this will mean that like you have a feedback cycle where you made a mistake and then like the network output is huge, the gradient is huge, and then he makes the network output even bigger the next one. So like, you would diverge very quickly. Okay. All right, so this brings us to this table I showed very briefly in the beginning, which describes MUP in general. So this table, the rows in this table are the hyperparameters, like the C starting, like for example, for your initialization and the learning rates, and then you also have in the columns the different parts of your network, so like output weights, hidden weights, input weights, biases, and then the entries tell you how to scale these hyperparameters in these parts of neural networks with respect to some notion of width. So here, fan in or fan out is the number of neurons going into or going out of that weight matrix. So it's a notion of width. So for example, like if you look at 1 over fan in squared or 1 over fan in here for the output weights, then this is just the same as the 1 over n squared and 1 over n here in the previous example. So the way you read this is the purple text plus black gives you UP, and then the gray plus black gives you standard computation. Okay. Like I think like so this summarizes like what is the right thing to do for essentially arbitrary neural networks. And this is really like one of the big reasons it's so powerful. It's like very universal scaling. It's kind of like Newton's law, right? It works everywhere. And likewise here it doesn't work just for transformers or just for ResNet. It works everywhere. So it's like something that will last for a long time. Okay. Any questions so far?
So the map from the initialization to the output, it's not Lipschitz, right? Because then also you can expect concentration of the level, not Lipschitz.
For like you mean from the initialization scale to the output?
No, I mean like you take a random initialization and just expect a certain output, but that map is not a Lipschitz.
That's a good question. I mean, I guess first of all, it depends on like what is the norm of the weights that you're putting on. Yeah, so so you cannot expect it to be Lipschitz in general, like for like arbitrary weights. But like in some sense, like if you sample randomly, then like I think you're gonna be in somewhat Lipschitz regions. So it's like it's like some self-averaging effect. But if you adversarially perturb the neurons, the weights, then in general, you can be very non-Lipschitz. I mean that's yeah. 5 minutes. Yeah, okay. So let me just maybe briefly talk about the theoretical mathematics behind this. So like there's a very very deep mathematics behind this. But I want people to understand this as much as possible. So I make it very simple. But there's always like a hidden beast behind this, and there's a very beautiful mathematics behind this. So the way these things, this MUP is derived is really like so. So first of all, like you can consider all kinds of parameterizations where the way you fill this table is like any power of fan in or fan out with whatever. So there's a lot of different possibilities of how you scale things. And let me see. So essentially, like, you know, the question I was grappling with is, you know, how do optimal hyperparameter scale with the model? And you know, so you can consider all the possibilities of such scalings. And the point here is that, you know, to understand what is the optimal one, it turns out to be very fruitful just to consider all possible scalings of hyperparameters. And what you want to do is you want to, like, you know, take any scaling and then let withhold infinity. Then you can try to, like, see mathematically what is kind of limiting behavior I see in the neural network. Okay. And what happens is that you get a landscape of, you know, different infinite width neural network behaviors. And you can you know, so this is kind of the picture, and then you can pinpoint like which one is the optimal limit in some sense. So for example, what this picture shows is like the all possible parameterizations and their infinite width limits. So when you essentially, the point is that when you take infinite width limits, when the width is large enough, if you scale if you pick a random parameterization and you scale your network in that way, then when the width is large enough, like some defects will happen in the neural network. So for example, like if you pick a point, random point, you're most likely you're gonna get a parameterization that's unstable or trivial. So the training blows up, or training gets stuck in the translation when the width is large. And but there are more interesting ones in the space of parameterization. So you can actually get something like more non-trivial, where like the model of the function evolves according to some simple equations like this, and so on and so forth. And so, but essentially, you can see that, like, you know, there's always some defects with almost every parameterization except for one, like this maximal update or mup. And so that's how you know that, you know, things are like this mup really is the optimal way of scaling, because essentially if you scale it any other way, when the model is large enough, there's some like defects, some like catastrophe that can happen to the neural network. That means that you should not, like, you should not be like this way of scaling should not be optimal, because, you know, bad things will happen. Okay, so maybe let me just like finally let me show you this animation here. So what this is so on the right you have a space of parameterizations, a two-dimensional subspace of those space of parameterizations that has both mup and the standard parameterization, which is the PyTorch default. And then on the left you see like the curves that we've seen many times already, but certainly the way you scale the model on the left at any given time is provided by where the green dot is on the right. Okay. So for example, like, you know, only when the green dot is on mup, you see like the hyperparameters are stable, and the curves are not crossing. Right. But if you like shift away from mup, then like you can see that all the bad things. So this is just a very graphical and vivid way of showing that mup is the unique way of scaling the hyperparameters that preserves optimality. Okay, so let me just conclude. So, you know, taking a step back and looking at the history of science, you know, there's a famous article by Wigner called "The Unreasonable Effectiveness of Mathematics and Physics." And indeed, you know, there's mathematics has had some triumphant successes in understanding our universe. So for example, now we understand the world is comprised of four fundamental forces: and gravity, electromagnetism, nuclear and strong nuclear force. And we have two very successful mathematical models of these fundamental forces. The standard model models the three forces on the right, and then you have Einstein's general relativity that tells you how gravity works on large objects. But you know, everybody also knows that we haven't been able to combine them and arrive at this like holy grail, which is a theory of everything for for unifying all of these forces. And this, I mean, this story is still ongoing. You know, who knows what the final answer looks like. But in deep learning, we also have fundamental forces. We have width, depth, you know, training time, so on and so forth. And these are, you know, the dimensions on which we can scale our networks, our systems. And we also have some, you know, like initial successes for understanding these fundamental forces. So, you know, this thing I mentioned very briefly, but didn't explain tensor programs, is the underlying framework for deriving everything I pop up today. And like in some sense, it gives you as good of a theory for large width neural networks as possible, fixing everything else. All right, so this is kind of like, you know, like relatively describes gravity independent of everything else. But you know, these other fundamental forces, we have very little understanding in comparison. And the key question is, you know, like how can we understand like the way we should scale hyperparameters with depth, for example, with training time and so on and so forth. Or are there even like fundamental scaling dimensions? You know, like famously in the 19th century, people thought electricity and magnetism were different forces, but it turns out, you know, they're exactly the same thing, just two sides of the same coin, because of Maxwell's equations. So likely, you know, will be like many of these things are, you know, redundant and can be made, can be unified into a single theory. So right now, especially we're kind of at this inflection point in human history where we're potentially, you know, creating a new, you know, like a kind of new kind of intelligence. Like this kind of this search for a theory, everything for large scale deep learning is potentially going to be a center of this inflection point. So this kind of theory would ask, you know, how should you scale your hyperparameters with these fundamental scaling dimensions? Can you unify these dimensions into a single theory? And when you train a very large model, how should you allocate your resources across, you know, these different dimensions? So, you know, if you're a mathematician and you believe in or you believe in what I just said about you know, taking limits and stuff, then the roadmap is very simple. You for each of these nodes to the side, and take infinite size limits, you classify all the possible limits and you find the optimal limit. So like I said, I briefly gave you this picture for the infinite width picture, which was able to derive UP using this framework. And if you can do this, you can, you know, you can profit very handsomely, become very famous, you know, make very large contribution of using that. You know, like these taking limits and classifying limits are things mathematics is really good at. If you look at, you know, all the famous contributions that people cherish in the history of mathematics. So this is something that, you know, mathematicians are in a privileged position to contribute to. Okay, so I'll just end here. This is the QR code links to the paper that I made pop up today, and you can use UP today if you are doing deep learning. Thanks. Yeah.
It's probably very stupid, but you know, since you had analogies with physics all through your talk, the scaling that you showed us, that feels very much to me like a free field scaling in the language of physics. And we know in the study of critical exponents, there are more interesting scalings than free field scalings. There are interacting fixed points where correlations, variables are not independent, but there's some sort of
that's right.
So could you imagine that when you take these more larger sets of variables into account, you enter interacting field theories?
Yeah, I mean, so in some sense, yeah, so there's a very rich analogy between what's presented here and the field theory, like, you know, especially like renormalization. So like one way you can think about so one analogy you can make between, like, you know, this the scaling of hyperparameters is the following. Let me see those slides. I don't think I have it here, but roughly speaking, you can think like hyperparameters on the neural network side is like roughly like couplings in the field theory side, and the the kind of optimal scaling of hyperparameters is kind of like renormalization on the field theory side. So when you try to scale the model up and become larger and larger, it's kind of like you're going to a higher and higher frequencies on the field theory side. So so for example, like a hypothetical scenario in QCD is suppose 10 years, 20 years ago, you were doing lattice QCD and you computed some couplings, okay? And but like the lattice size cannot be too big because we don't have the computation there. So when we eventually now when we do the experiment again and try to get the couplings again, it's probably going to be different, right? Because the lattice size will be larger. But you can probably run renormalization or something to predict what the coupling for the finer lattices from the smaller or the coarser lattice. So that's analogous to training a neural network or tuning a neural network, get hyperparameters and then scaling it to the large. Right. So it's very similar.
Right. And your scaling was a very simple one.
Yeah.
Whereas
exactly. Yeah. So yeah. So that is also something I noticed, and it's very interesting why the physics normalization is so complicated. I think I don't have a very good answer here, but I think in some sense so one potential reason here is that you somehow so the insight one of the insight here is, for example, suppose you ask the question of can we just just use standard conversation, just predict what the optimal learning rate is, right? Just as you scale larger and larger. And like I said, that's suboptimal because the true picture is a very high dimensional picture, but you're restricting your attention to one dimensional space in here, and that one dimensional space, going away from the true optimum. So you can try to kind of predict what the optimal point looks like. But the function for that point for the optimal learning rate would be very complicated, right? I mean, so in some regime it can be very simple, but then as you scale, it will become complicated. So in my one possible reason for why physics is also very complicated is because in some sense the space of coupling is not the right space of coupling. You're in some sense we're being maybe too naive where we just consider polynomial operators and just put numbers in front of them.
And physical quantities specifically scale with those scalings, right?
Yeah.
So
yeah,
there are some things independent of how you're parameterizing.
Yes.
There's a nice critical exponent that can be measured in labs. It's complicated.
Yeah. So so there's definitely a lot of evidence for in the lattice case, you can predict the critical exponent and so on and so forth. So there's a lot of evidence that the current way physics are being done is probably right in a lot of ways. Anyway, I'm not a physicist, it's just speculation, right? So but it could be in other regimes, for sufficiently high energy, things break down, and you need to consider other outside of polynomial operators.
Thank you.
But somehow you're saying that there's a lot of independence in your system, even when you engage in descent, you maintain independence.
Right.
And
That's
you're
completely
saying there's interaction.
I was hoping it was in the room for interaction.
Okay, so maybe so I mean, I think you can think about it in a couple of different ways. So so you can think about interaction between weights of different parts of the neural networks, input weights, output weights, hidden weights. So in that sense, this is everything's interacting because you will, as you train, they will know about them. But I think what you're referring to is that when the width becomes large, the neurons become quite somewhat independent.
You have some numbers that were effectively independent.
Yeah.
That's free theory.
Yeah. I mean, I'm not sure that's a fruitful analogy, but maybe just to answer your question directly, you can do a larger n expansion in some sense, where you can keep track of what the correlation is for finite networks. And then I guess in your sense you become correlated, but yeah.
Thank you.
Yeah. Any questions?
So how are practitioners using all this, with catching on?
Oh, yeah, I mean, like all the big players. Yeah.
Okay, thank you very much.